right. Welcome everyone to the final day. Those of you who have managed to get in at 9 a.m. on the fifth day of this, but also for the summer school students, this is like day 10, right, of stuff. So congratulations. So our first speaker today is Robert, and he's actually a professor of physics at Caltech and also research scientist at Google Quantum AI. So earlier in the week, I guess we heard about how LLMs are going to take over and make us obsolete, and now you're going to tell us how quantum algorithms are going to take over and make us obsolete, I guess, something along those lines. So take it away.
Yeah, thank you so much for your introduction. I'm Robert. Today I'll be talking about generative quantum advantage. This talk will contain, the majority of it is in a theory paper by me, Yunxia Liu, Michael Broughton, Zeph Landau, Isaac Kim, and also Jerry McLean. But I will also talk about an upcoming work that performs an experimental demonstration of some of the theoretical results that we have with Michael Broughton, Norhan Essa, Harman Navin, Ryan Babouche, and Jerry McLean. So as we all know, generative models has become very popular nowadays. Most of us are using it every day. And on a high level, a generative model is a model that can learn from some given data set, such as the entire internet, to generate new outputs for a given input from some probability distribution. So for example, we can put in some inputs, which is our question, and then we hope for the generative model to generate the correct answer for our question. But the answer can take many forms, and all we want them to do is to be able to sample accurately from some correct distribution. More precisely, we're given a data set containing of a bunch of inputs and outputs xi, yi, that are sampled from some unknown conditional distribution p of y given x. So for example, the input x could be all the texts that come before a specific token, and then yi corresponds to the token that we wanted to sample for the next word. And the goal is to learn from the given data set such that after learning, we want the model to be able to generate new output y for any given input x. So the input can be arbitrary, and we want it to be able to generate the correct one according to some unknown hidden distribution. In the case of large language model, that would be the distribution over human languages. But all of these can be defined without any notion of quantum computing or classical computing. It's just an abstract mathematical form. However, if we now consider all of the possible generative models that can be created using classical machine versus all the possible generative model that can be created using quantum machine, we can now compare between these generative classical versus quantum AI models. And informally, one could define generative quantum advantage as the following. That is, there's a task such that a quantum computer can learn from some data set in order to generate the desired outputs for any given inputs, such that when compared to the classical AI model, for example, it could have reduced sample complexity, meaning that it can learn from a much smaller data set to achieve the same performance. Or if it's using the same data set, like the entire internet, we hope that it could achieve, for example, higher accuracy. Or in the case when the accuracy and the sample complexity are the same, we want the AI model, the quantum one, to be, say, exponentially faster in terms of the learning, or the generation, or the inference time. Or it can produce outputs that are simply impossible for classical computers. So on a high level, generative quantum advantage could take multiple different forms in terms of sample complexity, in terms of higher accuracy, in terms of faster computation, and any of which will constitute a generative quantum advantage. And in a way, they are the same thing. For example, we can say, fix the learning and the generation time. Then in that case, the quantum AI would essentially achieve a higher accuracy. Or if we fix the same prediction accuracy, then it would achieve a much better learning or generation time, etc. So in a way, all of these criteria are closely connected. And this generative quantum advantage is something that we would be interested in having, as generative models have become a very important part of the current technology. So previous to this, there have been a wide range of different notions for quantum advantage. There's quantum advantage in computation. The most well-known example is factoring. We can factor very quickly. There are also various other quantum advantages, such as quantum advantage in sensing. And all of those are quite different. And here we would like to focus our attention on this new notion of generative quantum advantage. So the main question can be stated as the following. So we would like to understand if there are families of unknown distributions, probability distributions, mapping classical inputs to classical outputs. One can think of the classical inputs as some bit string, and then given such a classical inputs, we wanted to produce some classical outputs according to some distribution, such that the first criteria is that the quantum computers can learn efficiently. And then second, it can also generate efficiently. Suppose the learning and the generation are very efficient. And finally, we want the classical computers to be unable to generate efficiently. So the question is, does such a family exist? And if they do, how can we design algorithms running on quantum machines in order to essentially demonstrate such an advantage? So what I would like to do for today's talk is to provide a series of progress that essentially lead to the resolution of the previous question in the affirmative. So first, I would talk about, in the first part, I would talk about this notion of generative quantum neural networks, which have been studied in the literature. However, people have run into a wide range of different challenge, but there's one specific one that was very detrimental, and hence, to date, people don't really know if, like prior to this, people don't really know if generative QNNs are of any use. And then second, I would talk about how the challenge can be overcome, and we can efficiently train and learn generative quantum neural networks. And finally ends with a sneak peek of our experimental results in an upcoming paper. So let me begin with the first part on generative quantum neural network. So recall the task is as follows. We're given a data set of input-output pairs, and the goal is to learn a model such that given a new input, we can produce and generate a new output, Y. And in the literature, in the quantum machine learning literature, people have been studying this concept called a generative quantum neural network. And broadly speaking, one can define them as follows. So essentially, we try to utilize a quantum neural network to define a generative model. And broadly speaking, the framework looks as follows. So given an input X, we will try to encode that input X, it's a classical input, into a quantum state, given as psi X, as well as a measurement basis Mx. And what we're going to do is we're going to consider having a trainable part, like a trainable quantum circuit, C beta, where beta is a high-dimensional vector corresponding to all the parameters in the trainable parameterized quantum circuit. We're going to apply that circuit onto our initial state. And then after applying it, we're going to measure the output state in the basis Mx. And by performing so, we will be able to sample a bit string Y according to some distribution, Py given X, as well as beta. So by changing the parameterized quantum circuit, we will be able to change how the conditional distribution look like, this Py given X. And that's probably speaking how a generative quantum neural network look like. And one can effectively see the relation of this to a standard generative classical neural network, where given some input, we'll try to design some methods to encode that input into certain representation. And after that, we will apply some trainable parameterized layers onto the input. And then from the input, we'll obtain some output. There's no notion of measurement, but we will obtain some output, and that output essentially corresponds to the sample of the next token, for example. So one can think of this generative QNN as essentially the quantum version of a generative classical neural network. And a very basic feature of this is that it's not hard to prove that a generative QNN is universal. So what that means is, as long as the quantum circuit is big enough, then we can prove that for any distribution py given x, there's always a way to choose the high-dimensional vector beta such that it approximates this arbitrary distribution. So a generative quantum neural network is also a universal approximator, so that's a basic feature. But being a universal approximator doesn't really mean much, because it just means this model is big enough so it can handle all kinds of conditional distribution. And furthermore, generative classical neural network like transformers are also universal. So from that angle, universality doesn't imply anything about quantum advantages. However, that indeed says this is at least a reasonable model and a sufficiently expressive model for us to consider. In practical terms, just having some very big model is not very good, or it's not sufficient to achieve any kind of advantage. In order to achieve generative quantum advantage, we also want the generative QNN to be, for example, trainable, and after training, it can predict very well, etc. So there's all these other criteria that comes up. And in order to satisfy some of these other criteria, the community has been looking at a more restricted model called a generative shallow QNNs. So shallow quantum neural networks are quantum neural networks that only has constant depths. One can think about this as a quantum version of, for example, multi-layer perceptron with a constant number of hidden layers that would essentially, if you quantize it, it would essentially correspond to these shallow QNN models, whereas the depth is just a constant, like maybe it's a depth of 10, a depth of 20, or a depth of 100. It's a fixed one. And because their depth is fixed, in a way, these models are much more simpler. They're much more restricted, and hopefully much more trainable. But despite their simplicity in the restriction coming from the shallowness and the depths, they are known to be very powerful. So they're surprisingly quite powerful. So for some of you that have thought a bit about like quantum mechanics and entanglement, we know that when there's a dynamics, like a quantum circuit, that is low depths, like very short time, then all the entanglement can only happen very locally. So for example, under this depth 3 circuit, all the qubits down below would only be entangled locally, so they'll only be talking to each other. So intuitively, it would have felt like the state that would generate out from such a shallow quantum neural network will have very low entanglement, which is indeed true. And as a result, it will not be able to exhibit any kind of fundamentally quantum mechanical effects, and hence would be classically easy. However, what was shown in the recent decade is that under standard computational and cryptographic conjecture, one can prove that there are shallow QNNs that can generate highly non-local and classically hard distributions, such that this distribution will be impossible for any polynomial time classical algorithm to generate. And the rough idea behind this claim is the following. So basically, similar to in quantum mechanics, there are often times where we can trade off spatial dimension with temporal dimension and do path integral in a different way. By utilizing ideas of quantum teleportation and measurement-based quantum computing, one can show that if I have, for example, a two-dimensional shallow QNN, so think of the qubits being laid out in a two-dimensional grid, and the time is flowing out of this plane, and it's only evolving for a constant amount of time. Then this 2D shallow QNNs, and we can train the parameters inside. So this 2D shallow QNNs, one can prove that corresponds to a 1D deep QNN. So one of the spatial dimension, which is, for example, this, can be transformed into a time dimension. And we can show that when we perform a measurement onto the output state of this shadow QNN, we can simulate that measurement or that measurement essentially corresponds to first sampling a random one-dimensional deep QNN, and then generating an output from a 1D deep QNN. So the proof idea for this claim is that if such a classical algorithm exists, then because of this duality between 2D shallow QANNs and 1D deep QANN, we can show that this classical algorithm can be used to sample deep quantum circuit, as well as generating an output from these deep quantum circuit, which is believed to be very hard. And furthermore, this task of sampling a deep circuit and getting an output from it, one can establish that fact by relying on two widely believed conjecture. The first one is that there are some counting problems that are extremely hard, sharp P hard. And then the second is that polynomial hierarchy doesn't collapse. So it's two well-known conjectures in complexity theory. And by relying on them, one can establish that a 2D shallow QANN is computationally hard or can generate distributions that no classical algorithm can. And this phenomenon also applies to higher dimensions. So if I have a 3-dimensional shallow QANN, like a block of qubits that are interacting, like a cube of qubits interacting, one can prove that such a 2D shallow QANN can be mapped into a 2D or a 3D shallow QANN can be mapped into a 2D deep QANN. So always one can trade off one spatial dimension with a time dimension. And for more detail, one can take a look in these two papers, which are two very nice papers by researchers in our community, which establishes this fact and write out everything in a much more clear fashion. So given the power of generative shallow QANNs, it raises the hope that maybe we can use them to achieve generative quantum advantage. And prior to this work, there have been an extensive amount of previous results that study this problem of how we can learn and train shallow QANNs for various generative tasks. However, if one look into the literature, a lot of the things that they said is that it's mostly negative result, or the thing they prove is mostly negative result, in the sense that they show that due to a wide range of different issues, no efficient algorithm for learning shallow QANNs exists. And one of the main problem is the following. It's due to bad optimization landscape. So if one look at the loss function, the loss landscape that comes out of shallow QANN. So here this plot is an actual landscape plot when we try to train shallow QANNs for some simple generative task. Then a 2-dimensional slice of this high-dimensional landscape looks something like this. So one could note that these shallow QANNs do not exhibit barren plateau, which means that it do not exhibit exponentially small gradient on the landscape. However, it's very rigged, and whenever we start from somewhere, it would easily get stuck in this local minima. And when we try to jump out by applying some stochastic random noise, we would just jump into another local minima, and it is exponentially unlikely to go to the actual global minimum, which is at this point. And furthermore, this is just a 2D slice. In the actual loss function landscape, it's much bigger, and the landscape still looks like this. We can also zoom in a little bit. Even if we zoom in by 5x, we see that the global minimum is over here. But even nearby, it still looks very rigged. So when we start from this point, we might just go into this local minima shown here and fail to essentially find the global minimum. So due to the bad loss landscape, gradient descent and all other methods easily get stuck and fail. So if we go back to this question, if we look at shallow quantum neural network, we can see that first, quantum computers can efficiently generate outputs from distributions defined by shallow QANNs. It also exhibits the behavior that classical computers cannot efficiently generate due to the hardness result that I claim. However, the main thing that people have been running into, the main challenge that people run into, is that due to the bad loss landscape, we don't know how to efficiently learn and train these shallow QANNs. So quantum computers cannot efficiently learn from polynomial amount of samples. And hence it raises this existential question, which is, generative QANNs are computationally powerful, but could they be fundamentally hard to learn as the price to pay for their beyond classical computing power? So in the next part, I would like to say that actually the challenge could be overcome, and there is a way to efficiently learn any generative shallow QANN. So the idea is to change the way we parameterize things. So previously, what people do is we parameterize each of these gates. But instead, we will define a notion called parameterization by local inversion. So the idea of this is the follow. Suppose we have some n-qubit unitary U. It doesn't have to be shallow. It can be a very deep circuit. We say V1, another unitary, is a local inversion of U for qubit 1 if when we compose them, it becomes identity on the first qubit and arbitrary thing on the rest. So it locally inverts the first qubit. We can similarly define V2, V3, and so on. And an important fact that we proved in our recent work is that given an n-qubit unitary U, these local inversions actually uniquely determine the unitary U. And this holds regardless of how deep the circuit is. It's a fact that always apply. So note that this is a priori not clear because, for example, in quantum state, if we look at the local reduced density matrices, they don't uniquely determine the quantum state, but these local inversions do. And here's a pictorial proof. So what we essentially do is we assume that we know what these local inversions are, but we don't know what the U is. So U is unknown to us. And now what we are going to do is we're going to design a method that allows one to sew together these local inversions to form the n-qubit unitary U. And the idea is this. So we start out by having two n-qubits, n of which is just maximum state, and the other n is in some pure state. What we do is we imagine that this unknown unitary U is being applied to the maximum state. So the reason that we can imagine this is because applying any unitary to a maximum state is still a maximum state. So this is just in our imagination. It's not actually physically there. And what we're going to do is we're going to use the local inversion to essentially turn this thing in our imagination into physical reality. So first we will apply V1, which essentially opens up an identity on the first qubit. We will then dispose of it by tracing it out. Now we have one less qubit. We rewire it by taking the first qubit of an arbitrary input state psi into it. And now we implement V1 dagger again. So on the dynamic side, on the quantum unitary side, we just implement U followed by V1 followed by V1 dagger, which is equal to U. So it now heals back. And what we can see is that by doing these 6 steps operation, what we have to do is we have initially this U is just in our imagination. But now suddenly we can plug in the first qubit of any state into this imagined U. And we can do the same also for the second qubit by utilizing local inversion for qubit 2 and the third qubit and so on. And until the very end, what we have essentially established is we have sewed together them to form the n-qubit unitary U. So initially, U is just in our imagination, but by utilizing these local inversion, we are able to essentially turn this imagination into physical reality and then apply it to any state we want. And that essentially shows that local inversion can be seen as a parameterization of a quantum unitary. And the key algorithmic idea is that in order to train or learn an n-qubit generative QNN, what we are going to do is instead of training all these individual gates, we're just going to train and learn these local inversions instead. And the main idea is that training these local inversions can be done all in parallel and all independently. And one way to think about what this parameterization do is it's a form of over-parameterization. So previously, the bad landscape actually occurs because this qubit actually affects things, all the things in its light cone. And this qubit also affects all the things in its light cone. And essentially, it creates a frustration in the system that causes a huge number of bad local minima to emerge. And by changing it into these local inversion parameterization, we essentially fixes this frustration issue, and suddenly we can train all of them independently. So going back to the landscape, so recall that this was the landscape, the actual optimization landscape when we train generative QNNs based on the standard parameterization. It looks very bad. Now, if one changes it into this parameterization by local inversion, the landscape looks much, much nicer, and it looks roughly like this. So it's not convex, but one can prove that it only has a constant amount of local minima. So if we just train it with some gradient descent, with some restart, then it will easily go to the global minima very quickly. And here's a more detailed kind of analytics or numerical results on this. So if one consider training a generative QNN of this size, then we see that using standard parameterization, the probability of success for a single gradient descent run decays exponentially. And the reason is because the landscape looks like this. It's just all very jiggly, and then there's a single global minima in the middle. Whereas on the other hand, if we use local inversion, such as locally inverting just one qubit, or we can locally invert a block of qubit, then the landscape becomes much nicer. It looks something like this. We can also zoom out a bit from this landscape, and together it looks like this pattern. So it ultimately will have this periodic pattern, because one can imagine in quantum unitary, it's a compact group. So it has this kind of spherical form to it. So when we kind of loop around, we would easily go back to the original point, even though the parameter is different. And as a result, typically it would have this kind of strip-like pattern, but note that all of these are global minima. So we can start from anywhere, and all of these local minimum are global minimum. So that's all fine. And building on these ideas, we can prove that any unqubit generative shallow QNNs can be learned in polynomial time, such that the output can be sampled accurately. And as a result, we can close the final kind of point and establish the following theorem, showing that there are families of unknown distribution such that quantum computers can efficiently learn, can efficiently generate, but classical computers cannot efficiently generate. And for the remaining time, I would provide a sneak peek on the experimental results that we have. So one of the demonstration utilizes 68 qubits on a 2D geometry. The device layouts look like this. And we're going to use this shallow to deep mapping. So we're going to train a 3D shallow QNN, but since our device is a 2D geometry, we're going to utilize the mapping to map the 3D shallow QNN into a 2D deep QNN, and then use the 2D deep QNN to generate new output. So that's the strategy we're going to deploy. And here's just a plot for how the kind of the error scales with number of samples. So as the number of samples increases, the error decreases, and at around 1 million samples, we will essentially achieve accuracy or the error parameter that is smaller than sort of the error that for controlling these devices. So at this point, at around 10 to the 6, we're already at a very good kind of error scaling in terms of the training and the learning part. So here's a result from the experiment. So here we consider how many different qubits in this shallow 3D QNN, which all get mapped into a number of qubits that's less than 68 on our actual hardware. And here we can see that if we're doing everything in simulation, when there's no noise in the quantum system, then we can learn perfectly. So XCB is a score that allows one to capture how well we are learning, and an XCB score of 1 is the best, and lower 1 is worse. So without noise, we can see that the XCB score just remains 1. However, on the experimental platform, there will be noise. So the XCB will still decay with respect to system size. However, we can also compare it with, for example, training a transformer or training XGBoost to learn a generative model. And by comparing with them, we see that for any given size, there is a much higher prediction accuracy compared to these classical state-of-the-art generative models. And on the other hand, we also utilize or we repurpose the experimental data from our previous experiment by Morvan et al., published in Nature. And from there, it corresponds to a much deeper circuit. And that corresponds to a much bigger shallow qubits. And from there, what we essentially found, so these blue ones, corresponds to training a 3D shallow QNN. And after training it very well, we run the trained model on our quantum hardware with around 70 qubits. And again, as system size increases, due to noise, the XCB would decrease. But we can also compare it with what would happen when we run it on using the best known classical algorithm on a classical supercomputer, like the frontier supercomputer. And one could show that, for example, if one uses, by various estimates, one can show that using, for example, 18,000 frontier years, so 18,000 years running on frontier supercomputer, the XCB looks like this red line, which, as one can see, initially it's very good because it's a classical simulation of the quantum computation. But then at some point it will start to fail, since we're limiting it to only using 10 to the 30 floating point operation, which is already huge. It would start to fail, and then suddenly it would drop to a performance below the quantum methods. So at this point, at this stage, around 34,000 qubits, we enter the regime of having generative quantum advantage. So other than this, we also establish generative advantage for the task of compressing physical dynamics. And in this case, the task is we have some target unitary. It might be some long time evolution that we're interested in. And when we try to implement that on a quantum circuit, it becomes a very deep circuit. We want the generative quantum neural network to essentially generate a much shallower circuit that implements approximately the same dynamics. So that was also a task that previously people have looked into, but essentially failed due to the problem of optimization landscape. But here we were able to utilize this idea of first decomposing QNNs into these pieces, and then train and locally learn each pieces, which using this local inversion idea, and then combine these pieces together to form the trained QNN. So the strategy that I just described earlier, if we write them out properly, it essentially map into a form that look like this. So we apply this U dagger, and we do some swapping, and then we apply U. And note that these U's are the local inversions. And now when we combine them in this two-layer, we will be able to form the trained quantum neural network using this suing technique. So here is just some sneak peeks to the experimental result that come out of it. Essentially what we showed is that even when we go to some extremely high evolution time, like 23,000 evolution time, we are able to essentially train a shallow generative QNN to essentially match the same unitary dynamics and implement that on our quantum device to match the ideal performance or the ideal kind of observable of evolution using our quantum hardware. So to conclude, in this work, we close the loop on generative quantum advantage. So previously, we know that there are quantum circuits that are easy to evaluate on quantum computer and hard to evaluate on classical computer. But the learning part was lacking. And by utilizing these new ideas on parameterizing quantum neural network, we close the loop on generative quantum advantage, showing efficient learning and generation of classically hard distribution. And using the quantum hardware, we experimentally supported this generative advantage over classical generative models like transformers, as well as the best known classical algorithms running on classical supercomputer using a large, effective, shallow qubit. And that's it for my talk. Thank you so much for listening.
Thank you. Questions?
Thank you. Thanks so much. That was really interesting. I'm asking a more basic question.
Yeah.
Before you get to the parameterization of local inversion, you mentioned like the basis of the logic was to go from a 3D to a 2D space, or from 2D to 1D. Mm-hmm. I don't think I catched how. Did you just change the direction of the time domain, or what happened there?
Yeah,
thanks.
That's a great question. Let me go back to this mapping that I described earlier. So this mapping was used to talk about the computational power of these shallow QNN. And the idea is as follows. So basically it's using this idea of quantum teleportation in this context. So if I have a shallow QNN, let's say on 2D, so each of these circles are qubits, and then each of these edges are gates. There's also single qubit gates that were being applied on each qubit. And now we just apply some very shallow circuit onto generate an output y. Basically, the mapping, how the mapping works is as follows. So we first look at what is the distribution of bits that was created in this bottom layer. And we can essentially prove that under certain parameterization, then this output will just be uniform. So all of these will, like, if one look at the output of y, like the measurement output coming from this circuit, this would just be a bunch of uniform random bits. But what the uniform random bits essentially do, so this is uniform, what it essentially does is it actually, so initially there are some qubits sitting here. Think of them as the O0 state. And now with this uniform random bits that comes out, this uniform random bits essentially performs a quantum teleportation because of these entangling gates that was happening. So the quantum teleportation teleports the quantum state at this layer into the state at this part before any gates. So one can think of it at the deep bottom level, it teleports a state around here into here. And then the same also apply in this layer. So if you perform this measurement here, it essentially again produces some random output, like a uniformly random output, and then it teleports the underlying state into this layer. So that exactly matches with what happens in this 1D deep circuit. We start out with some initial state, and now we apply some gate, and then the teleportation happens. So note that the CZ gates that appear here correspond exactly to the CZ gates that was appearing here. And then the teleportation happens at this slice. So the CZ over here causes the teleportation to appear, and then the state at this layer gets teleported into as an initial state at this part, and then it just keeps going onward. So the mapping essentially says by running or by measuring this 3D shallow circuit, it gets mapped to essentially sampling some 1D deep circuit, and then when we measure the last layer, it corresponds to this measurement over here. So if you look at the small arrows, there's these small arrows coming out over here. Those actually get mapped are exactly equivalent to those here, and then the final layer corresponds to those coming out here. So it's using this phenomenon of quantum teleportation in order to establish this 2D to 1D mapping. I hope that clarifies it.
Okay. Hello. Thank you for the talk. Very pedagogical. Thank you very much. So at the end, so when you presented the experimental results, I can see that the noise has a huge impact, which is not surprising. So I was wondering if you could extend your analysis to non-unitary dynamics in order to incorporate the noise in the model. For example, a Markovian noise, any model of dissipative system.
In a way, all the results that we described earlier, we are applying all the results that I described earlier into this context. But it is quite important that this parameterization of local inversion focuses on, or the target is a unitary dynamics. So the idea is we have, which in a way, even noisy processes, like a noisy quantum channel, we can purify it and become a unitary. It's just a unitary on a bigger system. So all dynamics are unitary, and this local inversion idea corresponds to applying to a target unitary or try to decompose a target unitary. And in order to deal with noise, there are multiple perspectives on that. The first is one can assume everything is noiseless and try to train it using the idea that I laid out, and then deploy it into a quantum computer that is noisy. And that's exactly what we do here. So for example, if we deploy it to a noiseless quantum computer, then we achieve this green line, which has perfect XCB. But if you deploy it to a noisy quantum computer, then the noise will inherently affect things. So the performance will start to decay, but it's decaying at a much slower rate compared to classical methods. An alternative way to think about things is, suppose I wanted to, if my target thing is already a noisy channel and wanted to train that and learn that, one way to utilize the idea of local inversion is to first consider the purification and then after purifying it, it becomes still a unitary, and then apply all the tools here in order to handle the noisy aspects of things. So these are two immediate ways of dealing with noise, but I would imagine that one can also come up with a more kind of specialized ideas that can handle noise even better.
Okay, thanks a lot for the nice talk. So we know currently, I think classical generative models, they are used to mimic real world distributions like image and also human text. Since, this shallow circuit generative quantum model have actual advantage you show here, we wonder that looking forward, if we want to use this for real world data, do you expect in certain regime of real data, first whether it can be captured by such a quantum generative model, and also which field you think have this quantum advantage there?
Yeah, that's a good question. So here, this is just showing, as stated in the main question or this main result, that there are families of distributions that satisfy. But then the next question is this distribution or does things in this family appears in the real world? Or if we focus only on real world distribution, then does this three criteria still hold? So for human language, it seems less likely. I don't expect my brain to have any quantum mechanical effect. So human language, even though some researchers have still been studying that, but I'm not entirely sure on what would pan out. So in that realm, like human languages, I'm not sure if there will be a large advantage. However, one could also imagine generative tasks in scientific domains, like in chemistry, like in material science, like in places where there's naturally a quantum mechanical origin to the phenomenon that we're seeing. Then in those cases, one could hope that the distributions that we would like to learn will exhibit these advantages that I described here, which seems natural. Actually, for example, when I talked about this hardness result or the computational advantage result, what they essentially wanted to, or what this emerges initially was in the context of trying to understand short-time Hamiltonian dynamics. So just some local many-body dynamics and evolving for a short time. We now just measure it. Then does it create distributions that are classically hard and has quantum advantage? And what they essentially show is that there is a quantum advantage in that context. So one could imagine that in various many-body systems, when we perform measurement on them, they will generate distributions that are inherently classically hard, and we need to use these generative quantum neural network to capture it and to learn it.
Thank you.
Thank you very much for the talk. I had a question very similar to this one, but sort of asking a little bit deeper, are these, in this quantum advantage, does it mean that there does not exist a polynomial time approximation for these? Let's say I'm interested in generating something that's Wasserstein distance epsilon away from the distribution, from this hard distribution. Is it provably impossible to have this, or are most of these still sort of approximable with a classical circuit?
Yeah, so actually when I say no polynomial time classical algorithm can generate the distribution up to a small constant total variation distance. So in this statement, it already captures that notion. You cannot even approximate it. But of course, I should say that any claims about computation is going to rely on conjecture. We don't even know if P equals to NP or not.
No, I'm happy to accept these conjectures.
Yes.
Yeah. No, I was trying to understand about it. So if my sampling temperature was above this approximation distance, then it wouldn't make a difference?
You're asking if, what do you mean sampling temperature?
I have a distribution and I'm sampling from,
Yes.
When I look at the next word, I'm not taking the most likely one, but I'm sampling from a distribution. So now if I approximated a different distribution, which is sort of equivalent to the other one up to the temperature I'm using to sample from, I wouldn't be able to tell the difference between these two distributions.
So there's no notion of temperature at this stage?
No, just sampling, the sampling temperature.
Right. But I mean, like, how to say it? So the distribution here, there's no. Yeah, like, okay. I mean, if you consider some generative model like transformers, then in that model there will be sampling temperature. But you can tune that no matter what. But then all of them would not be able to approximate this distribution without breaking complexity conjectures.
Yeah. Okay. Good. Let's discuss that. I'm just saying that you might be able to get away with this because if you can approximate it up to epsilon or so, and then the rest is washed away by the sampling temperature that my transformer has anyways.
I see. Yeah. But no. So actually, even the XCB shows it pretty clearly. Like one cannot even approximate it to a very good degree. Like the XCB score being down here, like being 10 to the -3, basically means that it's just completely different from the distribution that was generated by these quantum models. So,
thank you.
Yeah. Thanks for the talk. So I mainly want to ask about like the 1D to 2D thing. So can I think of it as like, I mean, for the deep neural network, for a deep neural network, deep quantum neural network, is the challenge mainly come from the noise accumulated with the deep circuits? And is that the reason why we need to transform it into a channel QNN in order to have the quantum advantage?
So I would say, I guess you're asking like, why don't we just try to directly train 1D deep quantum neural network?
Yeah.
So prior to this work, we don't even know how to train shallow QNN. So I would say that's the first thing. So like this challenge is regarding that landscape, that applies to shallow QNNs. And if one focuses on deep QNNs, then even more problems emerges. So not only is this very rigged, but it's going to be exponentially flat, and it's essentially not trainable from that perspective. And so that's not due to noise. This is just due to the landscape when we tune the parameter inside these quantum neural network models. And the landscape looks very bad, and hence we cannot efficiently learn them.
And when you turn the parameter, like what is the analog? Like in classical neural network, we do
like
backpropagation.
Also has landscape, right?
Yeah. So like, what is the analog of backpropagation in quantum neural network?
Yeah. So it doesn't. So they doesn't arise here due to various reasons. Well, one very hand-wavy way of saying it is that these QNN models, they're exploring these exponentially large Hilbert space, and essentially when you whereas in classical neural network, you're just going to use some finite dimensional hidden layer. Like your hidden layer is say 100 dimension. So you're going to, so maybe your gradient is going to be 1 over 100 because you're a 100 dimension system, but 1 over 100 is not that bad. Whereas in these quantum models, it's inherently always operating in a space of exponentially high dimension, like its hidden space is exponentially high dimension. That's where the computational power comes from. But at the same time, because we're optimizing a model over exponentially high dimension, the gradient can be, say, 1 over the dimension, and that essentially makes it very flat. So that's one way to think about this.
But isn't the training process just a series of measurements, and why would those measurements be a challenge? Like if we don't care about noise?
Yeah, if there's no noise, this barren plateau still appear. That was a very surprising finding in the community initiated by Jerry McLean. But one can essentially prove that. And one way to think about it is that in these quantum models, due to the exponentially high dimension, things start to get decoupled. Like when you change any parameter in your circuit, when you tune it, it doesn't have any effect on your output, which is exactly not the case in classical neural networks. So this is a phenomenon that is solely kind of quantum mechanical, and I would say the origin of that is because of the exponentially large Hilbert space. Indeed, we're just tuning a finite number of parameters, like a polynomial number of parameters, and doing measurements on top of it. So there's no noise, so everything is exact. So note that there's also no noise here. This landscape is not due to noise. It's also just due to the fundamental physical nature of these quantum neural network models that gives rise to this very bad landscape. It was not due to noise.
Thank you.
All right, I think we're going to have to move on, so let's thank Robert again.